In the previous lecture, you actually wrote a pseudo character driver to handle a single device, isn't it? In this lecture, let's do one more exercise in which we are going to write a pseudo character driver with multiple devices. This is an exercise. You have to modify the previous pseudo character device driver to support 4 pseudo character devices. So you have to implement open, release, read, write, lseek driver methods, same as before, to handle user request. The pseudo character device, in our case, as you know, it is just a static memory area. You can use arrays here as well. Let's proceed. That means there will be one single driver or kernel module. I call it as PCDRV, pseudo character driver. And that driver is going to take care of 4 devices. Let's call it as PCDev1, PCDev2, PCDev3, and PCDev4. So the driver which we are about to write should manage 4 devices, or it could be more. You can consider it as manage n devices. There will be single driver managing all n devices. Remember that. You are not going to write 4 different kernel modules. There will be only one driver or one kernel module which is going to manage n devices. There will be only one implementation of open, read, write, release, and lseek driver methods. That also means the driver should first determine which device is being accessed from the user space to fulfill the request. That logic you have to build. So we'll see that while we code for this exercise. These are the device file names we are going to use for 4 different pseudo character devices. So in the dev directory, you have to create all these device files. Before implementing the driver, now let's discuss some of the design aspect of the device driver, how we are going to manage the information. Remember that every device has its own private data. In our case, a device is nothing but a memory area. We call it as a pseudo device, right? A memory area. What are the attributes or device specific information of our device? So the first thing could be a serial number. Every device may have its own serial number. A serial number could be collection of characters or a string data. Since our device is a memory area, so the starting address of the memory area is very important. That could be another device specific information. What's the size of that memory area? And the permission of that memory area also become device specific information. That means in our case, there are 4 device specific information. The permission could be read only, write only, and read write. This is how your driver is going to manage 4 different devices. Remember that in this exercise, every device represents a unique memory area. You can create the memory area either statically or by using a dynamic memory allocation. But let's stick to static allocation, that is array based, because we have not yet discussed the dynamic memory allocation in the kernel space. Let's push that discussion to a later point in the course. So we'll discuss how to use dynamic memory allocation API later. For this exercise, let's just stick to array-based memory. The user space will see your device files, PCDev1, PCDev2, 3, and 4. And the driver is going to manage 4 memory areas. The PCDev1 will be read-only in our case, and PCDev2 will be write-only. PCDev3 and PCDev4 will be read-write memory. This is the configuration we are going to use for this exercise. Let's say there is a user space application echo which tries to write some data to PCDev1. In that case, the driver should detect that and it should return the error code EPERM. That means operation is not permitted because this is read-only, right? In the same way, if an application tries to read from this device then only the driver should detect that and it should return the appropriate error code. And for these two devices, the user space application can read and write. Let's say there is a user space application, Echo tries to write some data to the PCDAV3. Then the driver should appropriately, it should copy that data to the right device. Driver should not put that data in the memory areas of other devices. That means the driver should detect to which device the request is coming in. That means the driver should detect, or it should understand, which device is being accessed from the user space, and it should process that request appropriately. So the driver should not corrupt the memory areas of other devices. So now let's move forward. Before implementing this exercise, let me also discuss about the data structure we are going to use for this exercise. What we'll do for this driver is, in the driver, we will maintain two structures. What are those structures? The first structure is going to hold driver's private data, and another structure is going to hold a device private data. Let's understand a structure to represent device private data. As I explained in the previous slide, every device has its own private data. In our case, the PCDAV device has a couple of private data such as start address, size, permission, serial number. We will put all this data in a structured format. That's why I'm going to include, or I'm going to create this structure, struct PCDAV private data, which has a couple of member elements to capture the device private data. The first member element will be a pointer to capture the start address. Next one is to capture the size, and this is a pointer to capture the serial number, which is nothing but a string of information, and this is to capture the permission. This structure also embeds our CDAV structure, that is character device structure, because in this case we are going to handle multiple character devices. Every device has to get registered with a virtual file system of the kernel. Since we are using, let's say, 4 devices, then we should be creating 4 CDAV structures. So that also means that CDAV structure is device specific. That's why it makes sense to keep that device specific information in the device private data structure. That's the reason why I embed the CDAV variable in the device private data structure. I hope that makes sense. So any private data, if you think it is specific to device, then you are free to keep that in the structure. We'll later see when we use synchronization related kernel objects such as spin locks and other things. That also, if it is device specific, then it goes into this structure. Let's move forward, and now let's explore the structure to represent driver's private data. In our case, driver is the one who is going to handle 4 or n number of devices, right? Character devices. That's why I include only 2 member elements in the driver's private data structure. The first one will be total devices, because since driver is handling n number of devices, so it is just to track how many devices being handled in the driver. That's the reason why I use int total devices variable. That becomes a driver's info, isn't it? The total devices will never become device information. It is not a device specific, it should be a driver specific. Now the next member element is nothing but device private data instances. So this driver is handling n number of devices. That means each device should have its own PCDAV private data struct variable. That's the reason I just created an array of device private data. Here number of devices macro represents number of devices. The reason for embedding PCDAV private data instances inside the driver structure is because driver is the one who is going to operate on the device specific data, isn't it? For example, driver is the one who is going to alter the memory address of a device to read or write data. That's the reason why we can create this array of struct PCDev private data inside this driver structure. I hope you understood about the structures what we are going to use for this exercise. And with that note, I would like to end this lecture here. So from the next lecture onwards, let's start coding for this exercise. I'll see you in the next lecture. PCDRV underscore private data. This will contain two member elements. One is total devices, and the second one is a instances for the device private data structure. Basically, since we are maintaining 4 devices, so I'll be using array struct PCDev private data. I would create a variable PCDev data of number of devices. So the number of devices, and this structure is not defined. Let's create another structure here for device private data. This is nothing but struct PCDev private data. First member element is the buffer. Second could be size. You can use unsigned for that. Size. And after that, what's the third one? Third one is serial number. And after that is a permission. I'm just using int. So I'm just using int everywhere because to keep this simple. You can also use typedef fixed integer data types like U8, U32, U16. All that will start using little later, but let's keep it simple. Here, let's use the struct CDEV. This is our device private data structure, and this is our driver's private data structure. We have committed a couple of mistakes here. This needs to be terminated. Semicolon, and we have to create one more macro. Maybe I would create here divine number of devices. Let's take 4. I hope you understood about these two data structures, and the driver is going to manipulate all these data structure. Let me stop here, and I hope you can complete up to here, and I'll see you in the next lecture. So please note that whenever you are coding for some project or some exercise, so always in between you should check your code by compiling it. Otherwise, if you finish that project and if you try to compile at the end, then you'll be getting too many errors and warnings, and it would take a lot of time to fix that. That's why you code for some functionality and then try to compile it to see whether the compiler is happy with your code or not. That is a good strategy to save a lot of time. I would like to compile this code, but before compiling, I cannot compile this right away because I have removed some variables and all. That's why I'm going to disable all these codes. For that, what I'm going to do is I'm going to every method, and I'm just disable this code by using if and end if. This is a read function, isn't it? I would just return 0 here, and this is a write function. Now let's disable the code, and if so, this is a write function. Now for a time being, let's return no mem, and let me disable open as well. Need not to disable open because we don't access any variables here. Release also, you can leave it as it is. These things will remain, and these are some global variables. We used it for our previous exercise. Let's take a look into the init function. I'm going to disable everything here. I would just keep return 0 here, and I would like to disable this as well. And here I'm going to change this name, a pseudo character driver, which handles n devices. Now let's try to compile this. You can go to your make file and change this to pcd_n. Let's make host. So you can see that we don't have any errors here, but there is one warning at 95. Let's see what is that. Here you have to return something, isn't it? Let's return for a time being 0. The code is fine. Let's get back to the project. Now let's move forward. There is a variable device number. This variable is used to hold the device number. Who maintains device number? Driver maintains the device number. So that's why instead of keeping this here, it would be good if you keep this inside the driver structure. I mean driver's private data structure. Because a device doesn't care about what's the device number. Device number is required for the driver, not for the device. Remember that. So that's why it makes sense to keep this in driver's private data structure. I'm going to remove these two lines and I'm going to keep this in driver's private data structure. And after that, CDEV we have already included in the device private data. Because CDEV is per device, that's the reason why I included that in PCDEV private data, not in PCDRV private data. So that's why I'm going to remove these two lines, not required. And after that, we have got two more global variables here. This is to hold the class pointer and this is to hold the device pointer. I'm going to remove this and I'm going to push this to driver's private data. Let's put this under driver's private data. So that makes sense. After this change, let's compile. Everything is fine. Let's get back. Let's move forward. So now let's create a variable of struct PCDRV private data. And let's initialize the device specific information in this field, PCDEV data. So let's start. I'm going to create one variable of PCDRV private data. I would just call it as PCDRV data. Let's initialize right here. Structure initialization. So first field is total devices is equal to, I will just equate that to number of devices, comma, and after that device number we are going to allocate it. That's why I cannot initialize this here. Class PCD, device PCD, all these things we are going to allocate it using their respective kernel APIs. I cannot do that here. Let's initialize all 4 devices. And the next one is .pcdev underscore data is equal to, this is an array, isn't it? So, and it has got 4 array elements. We can index those array elements by using the index 0, 1, 2, 3. Let's initialize the first index, that is 0th index. For that, let me open the curly bracket here and let's go to the next line. So let's access the 0th index by using square brackets is equal to, now every element has got different member elements because every element of this array is of type this one. It has got various member elements which we are going to initialize now. That's why let's open another curly bracket here and now let's initialize the very first member element, that is buffer. So which is equal to, the 0th device buffer is nothing but this one, device buffer PCDEV1. Let's equate that here. So let's use that address here, device buffer PCDEV1, comma, the next member element is size is equal to max mem size PCDEV1, comma, what is the macro? Mem size max. So sorry about that. mem size max, and the third one is serial number is equal to, so let's give some string value. Let me give PCDev1 XYZ123 or something like that. Next one is perm. For the perm you can use any number or identifier. Let me just use 0x1, which indicates this is read only, because the first device is read only. And after that, CDEV. CDEV we need not to initialize because we have separate APIs for that. Actually, this ends the initialization for the first device. Let's close this. Now you have to give comma and you have to start the next element here. But before that, let's end this initialization. I'm going to close this, and I'm going to close this main structure as well. And here you have to give semicolon. If you consider this structure variable, so this is the first member element and this is the second member element for this structure. This completes the first member element initialization, and here this completes the second member element initialization. Of course, we have more devices to initialize. Let's do that later. But this actually is the second member element for this structure. That's why I have opened a bracket here and closed here. That seems to be good, and it is fine, no problem. Let's get back to the code. Let's do the initialization for the next device. What I do is I just copy this code and I'm going to paste it second time, third time, and the fourth time. That looks fine. So this is for the device 1, this is for the device 2, this is for the device 3, and here we have to change to PCDev2, and this is PCDev2, and this is PCDev2. In our case, the next device is actually write only, so I would write 10 here, and after that device buffer PCDev3, this is 3, and this is 3, and this is read write. I would give 1 here, read write, and this is 4, this is 4, this is read write. Now let me save this and let's check. That seems to be fine, no problem. So here this semicolon is not required, so even if you give that semicolon, it doesn't matter actually. But since we don't have more elements, I can remove this last semicolon, no problem. So in this lecture, let's implement PCD driver init function. I'm going to shift this if 0 to somewhere here. Let's complete this part. First of all, we have to dynamically allocate device numbers. We are going to use alloc chardev region. Here is a change. This device number you have to get from the driver's data structure. This would be PCDRV underscore data dot. Its address you have to give. Ampersand PCDRV underscore data dot device number. And this is the first minor. First minor we can start from 0, and this is number of devices. So we have now 4 devices. That's why we want 4 device numbers whose base is stored in this device number variable. I hope you are getting this. Let me show you that. So the alloc chardev region takes now it actually allocates device numbers dynamically for 4 devices. Please note that all those 4 device numbers will not get stored inside this device number variable. Only the base is stored. Let's assume this function returns the major number dynamically. Let's say it is 127. That's why this device number variable, actually it has two parts. It has major number section and the minor number section. So in the major number section 127 will be stored, and by changing the minor section number you can derive the next device. For example, if 127:0 is stored in this variable, then by changing this minor number to next one, that is 127:1, you get the device number for the next device, like that. That's why driver distinguishes between different devices using these minor numbers. Please note that. Code for this line. Here we are printing device number information, but we have got 4 devices. Now let's use a loop to print it 4 times, I++. So now let me declare I here. Device number, you can extract the major number by using major macro. For this you have to pass device number plus I, because to print the next device number you have to increment the minor count, isn't it? That's why I'm using plus I here, and here as well, device number plus I. And this device number, now it should be modified. You have to write pcdrv_data dot pcdrv_data dot. That is fine. Let's continue our exercise. Let me just remove this if, and let me paste it here for time being. Our next task is to do cdev init and cdev add. This we have to do for every device. We have got 4 devices, so we have to write all these codes in a loop now. And the class create. The class create need not be in a loop. So because only one time we create the class create, that's why this need not be in the loop. And after that, device create has to be in loop. For that, now let's remove these codes. Anyway, we have this loop, isn't it? So now let's open the loop here and let's put all these codes inside the loop. Let me just select here. All these codes now should come under the loop. And let me close the loop here. As I said, this class create should not be in loop. I'm going to remove it. I'm going to remove this. I'm going to keep that. First I do the alloc chardev region, and after that I do the class create. So here this must be pcdrv_data dot class pcd is equal to class create this module pcd class. That's correct. And after that, this is error checking, that should be same. And after that, here this pointer to error macro should take pcdrv_data dot class pcd. Let's check these codes. Here initialize the cdev structure with fops. Here for the cdev init, the first argument is address of the cdev structure, but the cdev is per device basis in this exercise. That's why I will be writing this like, pcdrv_data dot pcdev data of I dot cdev. I hope this line is clear. and this will be the file operations. So that means every CDAV structure is initialized with file operation structure. And after that, register a device with VFS. Here PC dev owner, so this will be PC drv data dot PC dev underscore data of I dot cdev dot owner. After that, cdev add. So here also you should write something like this: PC drv underscore data dot PC dev underscore data of I dot cdev. And here you have to mention the device number. So device number is PCDRV underscore data dot device underscore number. And we are adding one device. That's great. After that, this is error checking. Now let's go to the next one. The populate the sysfs with device information. So device PCD, this will be PCDRV underscore data dot device PCD. Device create class PCD. Class PCD will be PCDRV underscore data dot null device number. This will be PCDRV underscore data device number null. Now here you have to create different device file names for different devices. So it should be PCD dev 1, 2, 3, 4. Let's look at this device tree API once again. Let's look at its implementation. So here I have a reference device create, and look at the last argument. This actually takes a formatted string, a string for the device name. So this is a formatted string. That's why you can write something like this. Let's get back to the code. I would like to write this as pcdev hyphen %d comma, and here you can mention I. When this loop runs for the first time, this will be replaced by pcdev hyphen this value I, that will be 0. Like that it creates pcdev 0, 1, 2, 3. If you want pcdev 1, 2, 3, 4, then I think you should give I plus 1 here. And after that, here this will be PCDRV underscore data dot device PCD, and in the error checking, this will be PCDRV underscore data dot device PCD. Our loop ends here. Now let's move forward. Let's remove this if 0. So we have almost reached the end. Now let me remove this end if as well. Let me remove this return 0. If everything goes well here, then it would print module init was successful and it returns 0. Otherwise you have to do some cleanups. So we'll code this later, but before that let's fix these variables. So this will be PCDRV underscore data dot PCD, and you have to delete the cdev structure. Actually this you have to do it in a loop. Let's do that later, but before that let's fix this. This cdev should be ampersand PCDRV underscore data dot PCDev underscore data of I dot cdev. Unregistered child dev region, you will be unregistering 4 devices. Here you have to mention the number of devices. So let's use the macro number of devices, and you just print module insertion failed and you just return the error code. This cleanup is incomplete actually. I will get back to this later, but let's compile and see whether we have any errors or not. Make host, and we have one error at 232. Let's check that. Here it is. So this is PCDRV underscore data dot. All right. Make host, and we don't have any errors. So here I actually did one mistake. cdev init is fine, in the CDEV add, for the next pass, it has to be the next device number. That's why you have to do +i. That seems to be fine. And in the device create, this is a class pointer. And for the next pass, it has to be the next device. That's why you have to do +i here as well. So please note these corrections. Finish up to here. In the next lecture, we will fix this cleanup procedure because we now have got multiple devices. So that's why this cleanup procedure is a little different, and I will cover that in the next lecture. So now let's continue our discussion on this PCD driver init. We almost completed this init function, but we had to fix this cleanup things. First of all, let's start from the beginning. So if here the alloc chardev region fails, then we go to out. That's fine. And next one is if class create fails, then you have to clean up what you did here. That's why I would give the label here unreg chardev. So let's implement that. Unreg chardev, here it is. Unregister chardev region of number of devices. That's correct. And after that, here CDEV add. CDEV add actually executes multiple times, because let's say if this is a loop of 4, then there will be 4 pass. So the CDEV add can fail at any pass of the loop. So the same is true for device create. This also can fail at any pass of the loop. So we'll do something like this. It doesn't matter at which pass these APIs fail, you just clean up for all number of devices. That's why what I write here is, let me create a label CDEV delete, and here let me write the label class delete. If any of these API fails, then we'll clean up for all devices. That's why what I do here is, let me write CDEV delete here. This is a label for CDEV delete, class delete. I would remove this. First of all, let me remove everything. And here, let me first write CDEV delete and class delete. If CDEV add fails, then you have to execute cleanup for both CDEV add and device create. For that, I would like to use a loop, and I would start cleaning up from the current value of I. That's a loop variable. That's why I would just give a semicolon here. I is greater than or is equal to 0, I minus minus. I go in reverse. First I would do device destroy. Device destroy. And after that I would do CDEV delete. And after that, that is class destroy, sorry. So this will be our cleanup. It doesn't matter at what pass or at what stage you fail, you have to clean up everything. Let's complete this device destroy. Let me just search for device destroy. Here it is. You just have to give the class and this devt information. Devt here is the device that was previously registered. If the device that was not previously registered, suppose if you pass an invalid value here, that means if you are trying to do a device destroy without being previously registered or created using device create, then there will be no effect in this API. For example, if this value is invalid, then class find device function here would return this as null. That's why if this is null, then this code block has no effect. That's why you can call device destroy on an invalid device number. You can do that. Here we have to use class pointer pcdrv underscore data. This will be class underscore pcd, comma, the device number. The device number is pcdrv underscore data dot device number plus I. And after that, cdav delete. Let's cdav delete. Here you have to give the cdav address. Remove a cdav from the system. So if the cdav is not present on the system, then there will be no effect in calling this API. So you just have to pass the address pcdrv underscore data dot pcdev underscore data of I dot cdav. And after that, class destroy. Just have to pass the pointer. So class destroy pcdrv underscore data dot class pcd. That completes our cleanup procedure. Now let's save and quit, and let's check this code, and this seems to be okay. Let's code for our cleanup. Let me delete everything. I'm going to just copy what I did here, because cleanup procedure will be same like we implemented here. I'm just going to copy this. So here it will be I is equal to 0, I is less than number of devices, and I plus plus, and these two lines will remain same, class destroy, and after that we are going to unregister charter. Let's just create a variable int I. So that completes our cleanup function, and let's try compiling it, and it seems to be okay. We completed init and cleanup functions of our exercise, and try to complete up to here. And in the next lecture, let's start implementing the driver methods. I'll see you in the next lecture. In this lecture, let's implement the pcd open method. As you know, the open method of the driver gets called whenever the user space application tries to open our device file. In this open method, the virtual file system actually provides us the inode structure address of our device file, and also a pointer to the struct file. I think you already know this fact, that is, for every open attempt, the kernel creates the file kernel object. In this open method, the driver must find out on which device file the open was attempted by the user space, because we have got 4 device files, isn't it? You should find out on which device file the operation was attempted. This we can easily find out by getting the information from the inode, because for every device file there will be one inode. If you check the inode structure, here is the inode structure. This is a struct inode, and you already know that there are 2 important fields, that is irdev. This represents the device number. So by checking this number, we can come to know which device is being accessed. That's why let me create one variable here called int minor number. First, the driver has to find out the minor number. The minor number is equal to, you can use the minor macro inode, just dereference to get this field I underscore rdev. This macro gives you the minor number. As I explained before, the driver distinguishes between different devices using a minor number. So this gives the minor number. Let's print that information, and after that you can access device private data structure here. Why accessing device private data structure is important? Because in your driver, before handling any request from the user space like read, write, open request, There are two things the driver must do. First one is it should identify which device is being accessed, and it should be ready with its private data structure, because the private data structure is a structure where all the device specific information is kept, like its buffer, address, size, and other things. That's why it is very important driver extract the right device specific information. So our device specific structure is struct PCDev private data, isn't it? Let's create one pointer variable. Here data is equal to, now the question is, how do you access the device private data structure of this current device? For this, again, you can take the help of the inode structure. In the inode structure, you find another field called CDEV, iCDEV. Let's search for that right here. This actually holds the address of our per device CDEV structure. We can take the help of this pointer to access device private data. If you just take a look into our PCDev private data, there is a CDEV structure. So if I access this pointer, I actually get the address of this member element. And by using this member element, I can extract the container address. Who is the container of this member element? This is the container of this member element. That's why by using the address of this member element, we are going to extract its container. For this, we are going to use something called container of macro. Let's explore the container of macro. What's a container of macro? So this container of macro is defined in include Linux kernel.h. This is used to cast a member of a structure out to the containing structure. Let me explain what's the use of this container of. So I have a separate lecture to explain how this container of actually works. Maybe I will cover that once I finish this exercise. But let's briefly see what is the use of this container of macro. The container of macro helps you to get the address of the containing structure by taking an address of its member element. Remember that. As its name indicates, it gives you the container address of the member element of a structure. It takes three arguments actually. One is pointer, second one is type of the container, and the third one is name of the member the pointer refers to. It actually takes three arguments. Let me explain those arguments. Pointer, type, and member. The pointer is pointer to the member, and the second argument is type of the container struct in which the member is embedded, and the third argument is member. Here you should give the member name, remember, name of the member where the pointer refers to. Let's use this container of. Remember that we are using container of to extract this member element's parent structure. Let's get back to the open method. Let me use the container of. As I said, inode gives me the address of the device specific CDEV. That's why I'm going to use inode, and I'm going to dereference it, and I'm going to use iCDEV. This is a pointer, and the next argument is type of the container struct. What's the container struct? That is struct PCDev private data, and the third argument is member name. Member name is CDEV. This is a member name. After that, that private data structure is really required for our other methods. For example, for read method and write method. Remember that from the read method you cannot extract that. Why? Because there is no supply of inode. So the VFS doesn't supply inode to the read or write method. That's why it must be done in the open method. You have to save this for other methods. because other methods also want to operate on that device private data, isn't it? It has to manipulate, other methods also manipulate the permission or the buffer field, etc. That's why you have to save this. So where do you save this? You save this data inside the file struct, because once a device is opened, a struct file kernel object is created, and the same kernel object is passed to different driver methods like read and write. Here it is. Read and write, even lseek, all these driver methods receive the same kernel object. So that's why you save that device private data inside this struct file. So we can do that by using one interesting field in this structure called private data. So we'll see that. Let's search for struct file. Now if you just check this file structure, you can see that there is a field called private data. You can use this private data field in order to supply a device private data to other methods of the driver, such as read, write, lseek. Let's get back to the code, and what I'm going to do now is I'm going to use this file pointer, dereference that. Let's use private data field in order to store this pointer, pcdev_data. And after that, the open method also should check the permission, because for example, in our case, the pcdev1 device is read-only. That's why the user application should not try to open the device file of pcdev1 with read-write access. So the driver should detect that, and it should then report whether the open was successful or not. That's why the permission checking should be done in the open method. I will implement the permission checking later. For a time being, let me implement this check permission here. So check permission. For a time being, let's keep it void, and let's just return 0. The permission is granted, something like that. Once we finish coding for all the methods, we'll come back to this open method and we'll finish this check permission. And after that, the final line is, if the return is non-zero, then the open method of the driver concludes that the open was unsuccessful and return the error code. Check permission basically returns an error code or 0. So we'll implement that later. I think we have come to the end of this open method. And now let's save this and let's try to build it. The build is fine. So in the next lecture, let's implement read and write. I'll see you in the next lecture.